today we begin with group theory basics. But before we go to it, we need to clear up something that we did towards the end of the last class, which was about the equivalence relations. So, just to remind you, what we said was that there is some relation we specify, and that it has to be reflexive, symmetric, and transitive. So, those are the three properties. And then we said that we proved a theorem, roughly, not very rigorously, but we checked that this operation actually subdivides the group into disjoint sets such that the union of those disjoint subsets becomes the whole set. The one terminology I did not introduce last time was equivalence classes. The subset of elements related to each other by R is called an equivalence class. So, the subset of elements which are all related to each other forms one equivalence class. So, what we drew, this bag of potatoes we were drawing, each one is essentially one equivalence class. And our statement was that the group splits up into disjoint equivalence classes such that the union of those equivalence classes is again back the whole group. And here the reflexivity allows for equivalence classes of single elements. Okay. So, property R allows for equivalence classes with single members. So, you may have something that is related to itself, but is not related to anything else in the group. Then that will become an equivalence class by itself. And typically we will see in group theory, very often the identity element may end up forming an equivalence class by itself under some property that you specify. So, that will happen. There is one other terminology which we will again encounter later, but sometimes we want to think of each of this equivalence class as one element. So, the class, essentially, if you pick any one element from it, represents all the others as far as that equivalence relation is concerned. In that case, this set is called a coset space. So, this is a set of sets So, we will see more about coset spaces later, where when the equivalences are themselves more refined. Here our equivalence relation R is very primitive, but we will see more. So, more advanced kind of equivalence relations, and there the coset space idea becomes more important. So what we have drawn here is effectively the whole set and equivalence classes in it, or equivalently you can think that we have drawn the equivalence classes which make up the coset space. Okay, so now we begin with the so called group theory basics, and what we will do is we start thinking of some specific examples. Okay. So examples of small groups. So to quantify what is meant by small group, we give a definition of the order of a group. The number of elements in a group is called the order of the group. In a group, and we will often write the symbol G. Order of the group. And we often denote it as with modulus sign, the same symbol G which is which stands for the group, with a modulus sign is used sometimes. If we explicitly know the number of elements, we may just write n or whatever the number is, but if not and we are discussing generalities, then we may just write this. So this is called order of the group. Let us think of very simple group, the simplest group of order 2. Well, the most trivial one is group of order 1. This is a group that consists of the identity element. Right? There is nothing very profound about it. If you can probably think of some examples, but it certainly is a group, an element that multiplies, that under group combination gives back itself, its square is same, it is itself, then it is its own inverse, of course. So that is the simplest possible group. The next possible group is group of order 2. And here we can think of a simple example of 1 and minus 1 under multiplication. So the group operation is the usual multiplication. So we can see that minus 1 square, so 1 is the identity obviously, and minus 1 squared is 1, so minus 1 into it, minus 1 is its own inverse, and so on. Okay. So this is the simplest possible group. This group is sometimes called Z2 or Z2 as Americans call it, with this script Z, the script capital Z. As you know, the script Z is used to denote integers, all integers from minus infinity to infinity, including 0. And if you write something below, then it usually refers to a class modulo that many integers. So this group 1 minus 1 under multiplication is called Z2. You can also, so this is one example of the simplest group, and we can draw a table for it. Which is going to be a technically useful concept and device. So we may as well underline it, and we draw it like this. We list the elements here, E and A. So now I am being a little more general and just saying that there are some two elements. E, the identity has always to be there, and there is one more element which I call A. What can be the possible multiplication table? Well, E squared is of course E, and E times A is A times E is A, and A squared is back to E. So this is a group multiplication table. Now the point is that here I did not write 1 and minus 1. Now the table is more general than the specific example we had. And so we will soon see how the generalization is made to an abstract group. But this is a very specific example. There happens to be no group of order 3. So we next have group of order 4. Here let us think of a simple example of square which we rotate about the axis perpendicular to it by 90 degrees at a time. So if we have a square, so let us say that if I rotate by 90 degrees, so of course identity is no rotation, and let us say A is 90 degrees or pi by 2, B is pi, and C is 3 pi by 2. So this is a very simple example of a slightly more difficult group. We can see that it satisfies all the group axioms because it is closed, all the operations are closed. You combine any two of them, you reproduce another operation. So remember that the configurations of this square, you may even try to remember what the so call it A, B, C, D. Okay. So if you perform any operation, then the configuration will change. Okay. But the square is just a generic square. So the A, B, C, D label is only for remembering what happened to it. So we can see that the configuration will change. Do not mix up the configuration with the operation. Okay. So if I have A, B, C, D, let us draw a smaller picture. If I do operation A, it becomes A, B goes here, C goes here, D goes there. If I do another operation, it is still operation A, but now it becomes D, C, A, B. Okay. So this configuration now is rotated with respect to the original by full pi, but the operation just rotated it once at a time. So the configurations that you have in the space on which the group is acting is to be distinguished from the operation of the group. So of course we can write the whole thing together, that this is nothing but our element B. So we learn that A squared is B. Now in general, when somebody suggests you any, this is all very simple, but in general when you are suggested an example, it is best to enumerate the elements you have and then try to work out the whole multiplication table, and you may have to sometimes even make a little model. You may have to cut out a little square out of a piece of paper and then see what is happening. In this case things are very simple, so we can just write out the multiplication table. So E, A, B and C so this of course is E, and we can see that the top row and top column actually just repeats the labels above. Now A squared, as we just checked here, A squared is basically B, so we get B. If we already have B, which is a pi rotation, and then do additional pi by 2 rotation, we will get 3 pi by 2 rotation. So this is C, and then we are back, then we should have, you can see now, the only thing left is E. So obviously a pi by 2 rotation, 90 degree rotation combined with a 270 degree rotation gives you back identity. So that is how this row goes. And similarly, if we start with B followed by A, then we should get a C, right, and 2 B's is going to be identity because B is a pi rotation, and B times C will be equal to A because B is pi rotation, and then you do additional 3 pi by 2 rotation, you will get a pi by 2 rotation. So, that is equivalent to A. Finally, as far as the 3 pi by 2 goes, this times A will be equal to identity, right, 3 pi by 2 and additional pi by 2, and then 3 pi by 2 with a pi will produce an A, and 2 3 pi by 2 rotations will produce pi effective. So, it will produce 3 pi, but everything is modulo 2 pi. So, it will produce a pi rotation which is B. So, this is the multiplication table for our group. We are ready to say a few things. We say that we introduce some ideas. When we introduce an abstract group, this multiplication table by itself is completely abstract. If somebody hands you this and says this is my group, all you do is check in it that it does not conflict with any of the group axioms, and then you can accept it as a group. But what we do is we say that the table defines an abstract group. The square we had is the square along with the operations, geometric operations on it. We call it a space on which it acts, some operations and the space on which it acts. So, our square plus rotations is actually a set of operations and a space on which they act. So, this is the generic property of any group. You will, although if you are just given the multiplication table, that is enough to define the group. In practice, you will want some realization of it. So, this is called the carrier space. On which those things act. Now, this is called, this whole package in number 2, second dash, is called a realization. Finally, we have the notion of representation, which we will have lot more to do with later on. We can say that the set of rotations actually, so when we say representation, we mean a particular size vector space, a linear space of specific dimension on which the group acts. Now, here we have not actually laid out the linear nature too much, but you can say the 4 vertices or their location geometrically, we have only a geometric representation so far. In present example, we only have a geometric representation which consists of the 4 configurations. It is the set of the 4 configurations. Okay. So that is our representation space here. So we will have more to say about this a little bit later. I should just warn you that occasionally the way people use language, they mix up realization and representation because they are very close. Realization is the whole package, some space on which the group acts. So that whole package is a realization of the, it's like a concrete realization. Whereas representation is just the base space, the configurations of the base space that actually can be written more or less like a vector or a tensor, like a linear space. So we will have more concrete algebraic representations, we will see later. Representations as vector or tensor spaces. Okay. So we are going hand in hand, setting up some examples but also setting up some terminology. The next we come back to specific terminology. So next we discuss the possibility that so we can say generators. By generator we mean some set of elements which when raised to some power multiplied by itself or among themselves generate the whole group. Okay. So we already saw a trivial example. I have a 90-degree rotation. If I keep doing 90-degree rotation several times, I actually recover all the 4 elements of the group. So the idea of a generator is, so first we say some notation, a raised to n is same as a o a n times. So if there is a subset of the group such that the powers of its elements and their mutual multiplication gives back all the elements of the group is called a set of generators. The simplest case is when you have just one generator. A group generated by a single generator is called a cyclic group. It is like a cycle. It's like you multiply several times, you get all the group elements, and then you start again, right? In cyclic group, it must happen that you have one element, you start raising it to powers a times itself, thrice, a cube, a4. Eventually, it has to become identity because the total group size is finite and we have closure. So, if you multiply any number of times, you must get back group element, but the total number of elements is finite. So, eventually a to the power some p should reproduce the identity element. So, in such a group, a squared, a to the p is the whole group, and p is called the order of the element a which is the generator. And so I forgot to add that. So, where a to the p is equivalent to identity, then p is called order of the element a of this generator a. And we already saw that example because our group of this multiplications, this rotations of the, so this particular example, essentially the 90-degree rotation generates all the other elements. So, it is a generator and this is a cyclic group of order 4.